for the intro. Sorry for the somewhat of a switch up of the order of this, but I think this particular topic fits well within this session and with our discussion today. So no better time than the present. So my name is Scott Gayski. I'm from Wake Forest University. Today we're presenting an approach that we've done to develop full-body geometrical data for finite element models. So I'd like to acknowledge my co-authors and thank you all for the opportunity. One more note on the title slide here. This is work that is part of what is called the Global Human Body Models Consortium Project, which is a project that's centered on developing finite element models for injury prediction and prevention. So I want to start out with a little bit about the consortium itself and the mission statement, and that is to create and maintain the world's most biofidelic computational and human body model. So I think it's nice to sort of introduce this work to somewhat of a different audience, but when we talk about these types of models, we're really talking about injury prediction and prevention in an environment that normally our simulation duration is quite short. It's on the order of a quarter of a second or less. An environment where inertial loads are really the dominant factor in kinematics and not sort of the way that people want to move, but the way that they are moving due to their initial velocity and the changing velocity. We are, Wake Forest University, as I mentioned, we are the integration center for this. So our role in this project is multi-fold. We recruited subjects, we acquired medical images for those subjects, developed CAD data, and we are currently developing and validating a full-body computational model. This sort of schematic up here sort of shows these almost in hoppers, but what we've done is we've developed a fairly detailed CAD model of the human body that is very specifically tailored for this particular application. Provided that CAD to our body region model, COE, regional partners, if you will. These are universities that are involved in the project as well, who have meshed that geometry, and now we're putting that geometry together and validating this full body model. So this is a project with a global reach. This just gives you kind of a snapshot of who's involved, from Hongik University in Korea to INRAPS, which is now, I believe, called IFSTAR. It is an organization in France that oversees transportation safety, and as well as a number of excellent universities in North America: Wayne State, Waterloo, Virginia Tech, UVA, and Wake Forest. So also I wanted to give you all a sense of the project timeline. There are obviously human body models for injury prediction and prevention that have been out, released, and known to folks for many years. The development of this has been quite quick, though, and rather than belaboring every point here, we started with a kickoff meeting in the middle of 2008, and we're on track to finish up our male 50th at the end of this year. And this is really sort of cradle to usage. None of the data really, in terms of geometry at least, and mesh data existed prior to the beginning of this. So we really did target specific subjects, recruit them, scan them, etc. So let's get into some of the details of that process and our CAD development methods. We wanted to develop full-body CAD in the seated position, and we wanted to just focus on anatomy that was required for a set of what we call crash-induced injuries. It's an important point because obviously we know how complicated the human body is. And with some of our motion models that we have seen today, you sort of focus on the things that are pertinent to your application. And we've talked about even how, with the community at large, how do you make a model that was developed for this usable to a specific group over here who has a different application for it. And this would be a similar case where, as you see we go through this is very much developed for our particular application, and that is to predict a set of crash-induced injuries. Our approach was to utilize imaging data from multiple modalities, and what we mean by that is CT, MRI, etc. Recruited a single subject for a number of targeted groups, and we heavily relied on literature sources to validate and verify that data rather than looking at a population. And really that was a matter of getting to the end result as quickly as we could and as scientifically accurately as we could. These efforts were begun on the 50th percentile male. Somewhat of a busy slide here, but I tried to give an overview of our subject recruitment. This is a project that is sponsored by a consortium of automotive makers, and so one of the main sort of the key metrics we were going after in terms of these percentile individuals were the percentiles of crash test dummies that are currently in place. The thinking of this was that we wanted a model that was directly comparable to dummy results. So while there is much debate on the applicability of the 1975 or 1977 male, average male, versus today's average male, this was in particular targeted for the average male that was designed for the crash test dummies. We went beyond height and weight, however, when recruiting these folks, and for that we utilized Study from Answer, which was developed at Natick. We looked at healthy individuals between the ages of 22 and 44, and external anthropometry criteria that met or that was within 5% of the Answer study data. And you can see the individual metrics that we looked at. This was all just prior to recruitment. Following this, all subjects underwent a full imaging protocol that I'll describe in the next couple of slides. And even after that, we had radiologists review that data in depth to determine if the anatomy of that data was normal. And all of our subjects were, which was good for us so we can move forward. But we did want to make sure that at every step of the way we were checking this against what would be deemed normal. And we weren't developing this model based off of an individual who in some way, shape, or form was a large deviation from the normal population. So we talk about image modalities. This was a multimodality study again, and these were the modalities that we chose, and there are sort of strengths and weaknesses of each one. But when you talk about closed-bore MRI, the advantage is you can get high resolution, but you can also specialize your pulse sequence. So when you acquire this data, you can acquire it in a very specific way. You'll see in some of the images I'll show that we specialized this pulse sequence so that we could accentuate the borders between fat and muscle, and that aided us in our segmentation. In upright MRI, the same technology as MRI, but oriented in a vertical fashion so that we could get standing and seated postures of these individuals. So we had the same individuals scanned in MRI as well as upright MRI. And we could look at how organs shifted with regards to those postures. We took CT data using standard clinical CT that has a fast image acquisition time and very high resolution, excellent bone anatomy. And finally, I list here external anthropometry. We used a Faro arm to get landmark data as well as external body contours of the subject. So just a couple slides on each of these. This goes through just a sort of a sample of the image data that we took. This is, again, for all of our recruited subjects. We used an 8-channel body array coil as well as an 8-channel neurovascular coil, 3D FSPGR pulse sequence, which is fast slow gradient recall. Since I made us think about acronyms before, I'm not going to get away with saying what that was. Within the abdomen, you can see here again, we had good 3D renderings as well as very good definition between fat and muscle that we were able to use in segmentation. And then just, again, a knee scan with the same sort of quality. In terms of upright data, I'll just kind of talk through these. We took data in a seated and standing posture throughout the body, and these are just several images, but showing the neck with the head in the frantic plane looking forward, seated and standing, as well as the abdomen seated and a flexed knee. And these images came in very handy in terms of you would segment from our supine data, but use this data to actually align the segmented structures within this framework so that we were very confident in the placement of that data in the seated posture. And again, on the same individual, so this was done for the 50th male as well as the 5th female as well as the 95th male and 50th female as well. We combined image data sets using commercially available software, and so we could take each one of these. This is just a view through the transverse plane, rotate it twice, and we get something like this. Added up in the same using interpolation algorithm, and we get this very nice combined image slab that sort of provides us from the neck through the pelvis of where these organs ought to be. If you're familiar with radiology, you would look at this and say, well, the resolution of that isn't as good as I've seen in a supine MRI, but it was good enough to allow us to place these organs and really get a good idea of where they ought to be relative to one another. When we took low-dose CT, we had the individuals in a quasi-seated posture that would allow us to scan them such as you see here, which again allowed us to align that data with the spine as it would be curved within the seated posture. And this was again used for bone and posture replacement. So that sort of wraps up the imaging side of this. When we move to the CAD data, we used this image data to develop 3D CAD for our M50 model, and we essentially looked at 4 phases of that. These are outlined here in brief detail: segmentation, conditioning, assembly, and nerves. We used both manual and semi-automated atlas-based segmentation. We conditioned that polygon data so that we would apply symmetry where it was appropriate, remove any artifacts, and at this point we did a very extensive literature survey to ensure that the organs, vessels, et cetera, down to about 4 millimeters in diameter were all within published studies of how large they ought to be, their volumes, their relative placements, where that data was available. We assembled using our upright MRI and quasi-seated CT, and then finally applied nerve surfaces to our STL segmentations. We relied on the body's natural compartmentalization in order to accomplish some of these tasks. For example, structures of decreasing size and hierarchy were placed inside one another from segmented cavities within the upright MRI. And we sort of looked at this as our Russian nested doll approach, where we wanted to take advantage of that. It was sort of work that was sort of pre-done for us. And you can see sort of the mediastinum area of the heart, as well as a large abdominal cavity. And what we would do is place organs within these cavities to ensure that they sort of fit within this envelope before applying our nerve surfaces to them. So this is, again, just continuing with the compartmentalization and pulling back this in the scan I showed before in a coronal plane, but you can see how some of this starts to come together. Again, I'm sure that there are very accurate representations of the anatomy in terms of, or complete, I should say, representations of the anatomy in terms of teaching, et cetera. But we were really looking for getting some of the sort of major anatomical components in a model that was very directly created for crash injury research. So we verified these features with our image data. We conditioned and adjusted this hierarchy, or we conditioned and adjusted these to meet an anatomical hierarchy. So if when moving these into this plane conflicted with a harder structure like bone, then we would morph and change the soft structure to be more compliant. And obviously the advantage here is that organ placement is based on a seated posture. And we see this as an improvement over a lot of other models that have been developed for crash injury testing that were basically developed from supine scans only. So this is just a focus on the CAD data by region and sort of the final result of that. We have a very detailed brain model that again was driven by attempting to predict very specific crash-induced injuries to the brain. Very detailed representation of the muscles of the neck throughout the abdomen and thorax. You can see some of the major structures: heart, lungs, liver, spleen, pancreas, gallbladder, etc. And as well as through the lower extremity with the major ligaments and fiber cartilage of the knee itself. I do want to spend some time just discussing a lot of the literature comparisons that we did. I think this is sort of a key component of the work because we did base this scanning off of an individual. However, we really used him as a template rather than tried to recreate him specifically. So for all organs, we checked volumes. For bones, we checked cortical thickness. For vasculature, we checked diameter. For selected musculature, and again, we're not really, with the exception of the neck, most of the muscles are there for mass purposes, and they're modeled as soft tissues and not active. We checked volume, insertion, and origin, and with ligaments we checked area, width, etc. So you can see here for the liver, across a variety of studies, we were right about in the middle. We tried to focus on studies that were based on males only, and a lot of these, they were mixed gender, but either way, we did see very good agreement. With cortical thickness, we checked it not just in single areas of the bone, but in multiple areas as the literature allowed. Vessel diameters, again, major vessels that were targeted crash-induced injuries, we did verify, and muscle volumes, as I mentioned. So we know that there's a lot of current data sets versus existing data sets for this. And so I just wanted to go over some assessment of data sets used in modeling a mid-sized male and where we are relative to those. I think many folks here are very familiar with the visible human, with HUMOS, for example. But these are great data sets, and I don't mean to diminish their utility in biomechanics studies, but there are certain limitations to those. For example, with the visible human, the individual was in a supine posture. His height and weight deviated pretty significantly from the mid-sized male, and he was a cadaver at the time of the image collection. The same with HUMOS. This was an individual of advanced age, cadaveric data. There was lack of scan data. For this, it was a relatively unique attempt at doing a full body model. The individual was actually frozen in a seated position and physically sectioned. Those physical sections were then traced, and the model was recreated that way. Other sources include Digimation, Viewpoint Data Labs. These are provided only in the standing posture. Scaling is required. It's based on cadaveric data. Schneider's anthropometry of vehicle occupants, again, an excellent source. It was used to develop the dummies, but it's mostly or really exclusively external data. our current data set has multiple postures, specialized image protocol. We did use live subjects, and I plotted some of the sort of pertinent data here. Height's in the bars, weight is in the line. And you can see we're not deviating significantly from a lot of these besides the visible human, but we do sort of bring with this data set a lot of information that wasn't previously available. So moving past the CAD phase onto the mesh phase, each of these meshes, or each of these models were meshed by our partner universities. This is an example of work by both ISHS, Virginia Tech, and UVA. You can see they did an excellent job of creating meshes of this rather complicated geometry. Our job, essentially, in this project at this point is to integrate what we receive back from our partners at these other institutions. And so we're constructing a full body model from regional models. And I wanted to present a slide of some of the ins and outs of that integration. This is not by any means not a trivial task. We would receive these models, we would provide initial feedback to our partners, we'd assess general fit. For example, you have these sort of unnatural, I'm not saying that this method of developing a model was not a good idea, but sort of some of the things that come of that are folks tend to do things different ways. And so when we would receive these back, you'd see these sort of very difficult to fill voids, and we have to go back to our partners and say, look, we need to do a better job of dividing this line up and how we're going to divide the flesh in particular, which is a continuous structure, whereas a lot of these are not. But we had them redefine how the flesh was done. We aligned grade vessels in the thorax and the abdomen, for example, with the nodal interface. At the AO joint, we did some mesh refinement and removed some penetration of the C2. And of course, there's a lot of abdomen to pelvis muscular attachments that we have also been working on. So this is where we are now with our full body model. This is the second iteration of it. The projected amount of elements is about 2 million. The target delivery date for our FBM2 is August of 2011, with the final delivery of the FBM after another round of iteration at the end of this year, essentially. And you can see that the geometry that we provide has largely been preserved. In some cases, muscles were modeled as three-dimensional structures to provide mass and to provide an even distribution thereof. In other cases, they're modeled as 1D structures as needed by the expertise of the various COEs. This is just a movie sort of detailing that, and so we'll rotate around and you can see some of that structure, in particular with the neck. There have been a couple, or at least one model by Gayski that did try to tackle neck muscles with hexahedral elements. This is the first full body example of that. The brain detail has been preserved in its hexahedral elements as well. As we move through this, you can see a lot of the details sort of even in the forearm with the fibrous band between the radius and the ulna. And it's just sort of backing up. I wanted to give a view of what the model looked like with the flesh and with the flesh removed as well. But this is meshed, it is not CAD at this point. Just some details on the FBM model itself in terms of finite element concerns. The mass distribution we've looked at, and it matches up existing studies by McConville quite well. As you might expect, the majority of the weight is in the flex region. The total mass, without doing any sort of fudging of the densities that the folks used, summed up to just almost exactly what this individual's mass was, which is another indication that we're very much on the right track with this. This provides projected elements by region. The neck has an interestingly disproportionate number since they have chosen to, or we have collectively chosen to model these as 3D elements. You can see again the largest mass, the largest number of elements is within the flex group. And the element distribution type is here with the majority of the elements being solid. I did want to also include some preliminary results of this. This is courtesy of our partners at Virginia Tech and ISHS, looking at an abdominal impact with a full body model with a free back at 6 meters per second. And you can see here in the blue the model response versus the actual data from Hardy. Fairly good agreement for an initial run through our full body model. We're very encouraged by this. This is a pretty tough simulation to get through just in terms of not having element failure because of the large amount of deformation. And with that, let me just wrap things up, just marching back through what we talked about today. We began with a new set of images, CT, MRI, etc. We utilized that image data to create CAD for an assembled seated posture of over 400 parts. It was designed to predict a specific set of crash-induced injuries. This is a generalizable approach. We feel it's expandable, certainly to standing posture and to other genders and sizes. The M50 is currently in our integration and validation phase, and we're beginning work at our center on frontal and lateral validation for some literature studies. And our hope here is that models enhance our injury assessment capabilities. I know, again, if you look at what dummies can provide, this ultimately opens the door for doing a lot more. Obviously, it's ahead of a lot of validation work, but this is certainly where we're going. And again, the phase 1 is finishing up in December. So with that, I just want to acknowledge our funding sources. And a lot of folks in this room work for some of these companies who are involved in the consortium, and our university partners who have been instrumental in allowing us to get to this point. So with that, I just want to thank you all, and I'll take any questions.
Your the inertial properties and center of mass for your dummy, where did you get those, or how did you connect it?
We use a study by McConville et al. Who provided section planes based on landmarks. So we use the same landmarks to create those section planes and actually just section the FEA model. And then we have, even though it's discrete, you can calculate the center of gravity of that compared to what he got relative to where those landmarks were. And we saw, again, pretty good agreement with that as well. I didn't present the data, but we are working on it.
We're in Brian Corner and I, we're in the process with Chris Albury and such of redoing a lot of that data for human cadavers, for center of mass and moment of inertia, some errors in previous work, and correcting some of that in larger populations.
Yeah. We'd be really interested to see some of that data. What we are using, you're probably familiar with the McConville study, I'm pretty sure that they use stereo photo techniques to get the data that they had. And obviously, we can take the CAD body shell that we have, for example, and slice that and assume uniform density and get the values that way too. So we are actually calculating it either through FEA or through an assumed density. And those numbers match up pretty well. But we have seen some discrepancy in the literature, and chalk that up potentially to just the methods of how it was done before, but I'd like to talk to you about it now.
Okay, we got time for one more question.
Actually, 2 questions, but the first one I thought this one was on an LS-DYNA. Is that also going to be available in other codes?
Yes, it is. Currently, we are working with Hamburg University as a subcontractor to translate this to both PAM crash and radios.
Okay.
That follows the LS-DYNA. The LS-DYNA is first.
Okay.
Let's come later.
And then my second question, some of the mesh components, I noticed that there's, for example, the lower legs, quite a bit of irregularity between the element size. Was there a specific reason for that?
Let me go back to where you noted that.
This one here.
For example, here,
Yeah.
I think that there was a concerted effort it gets back to where we're actually looking to predict injury, that in this sort of very fleshy area that we were not looking for specific CIIs there. It's sort of an economization of we need more elements here, we need less elements there. We had some constraints on how many total elements we use. So I think that's the motivation for doing that.
But I mean, my question is, why don't you just kind of even it out? If you look at the flash part on the lower leg, the tibia, you see a few that are fairly large.
Right.
And a few, wouldn't that be a fairly simple step to kind of even that out?
I don't disagree with you that that would be a feasible step to do. Some of the mesh work, I hate to rely on this as an answer, but we have certain tasks that are within the integration center. Meshing of each individual component wasn't one as much as sort of the integration thereof. We did work very closely with all of our BRMCOEs to meet targets in terms of size of element or time step of elements, which is closely related to the size, obviously. And so, for example, the tibia was remeshed. It's an astute observation on your part because those were actually smaller elements in an earlier version, but they were increased in size to also increase the time step because we were getting a penalty from that particular group's model that was dragging the time step from the entire model down and it wasn't meeting spec essentially. So it is driven somewhat by practicalities of having a time step that's required, but also there's a lot of CIIs that were crash-induced injuries that were targeted for the femur, for example, so there's a very dense mesh there in order to capture that.
Okay, thank you.
Thank you very much.